Hey there. Welcome back. We are going to continue our little journey on the 2017 AP Calculus AB examination. We have finished Section 1, Part A, and we are now on to Section 1, Part B. Okay, you would have 45 minutes to do this. We'll take a little bit longer going through these problems in some detail. 15 questions in this part. So I'm going to break this up into two videos. We're going to do 8 problems in this video, and the next video we'll do 7 problems, okay? The good thing here, a graphing calculator is required for some of these questions. You now get to use a graphing calculator, which means the math will be a little bit more difficult. The concepts are still the same, but who cares if the math is difficult? You get to use a calculator. And just because you get to use a calculator doesn't mean you can use a calculator on every problem. What does that mean? They will ask you questions where a calculator will be useless. Okay, I mean, you can try to use it, but you really won't be able to, and we'll go over some of those as we move forward. Let's begin. I'm glad you're here. And number 76 is a prime example of a question. Even though it's under Section 1, Part B, where we can use a calculator isn't going to be of any help here. Let me explain. Number 76 says, the graph of a differentiable function f is shown in the figure above. Which of the following is true? And it looks like, okay, we have derivatives. Remember, derivatives are the same thing as slope. Okay, so we're going to compare all of our slopes. All right, looks like the slope at -2, okay, -2, -2, -2. The slope at 0, and the slope at 3. We're just going to compare these things. Okay, here's the slope at -2. Well, -2 is here, so here's the slope. All right, the slope at 0, x is 0 here, so the slope here. And where x is 3, so the slope here. All right, so we are just going to compare the slope at those 3 points. I have no equation. I cannot calculate it. A calculator does nothing for me here. Okay, so the AP exam, they're sneaky. They're like, you can use a calculator here, but really the calculator is useless. This is a very simple problem to do. You can tell the smaller values are on the left side, and they get bigger as they go because the less than. This is the biggest slope. This is the smallest slope. And this will be like the mid-sized or medium-sized slope, okay? I've got to look down my column and see which one is the correct. I don't know values, but I can definitely tell whether the slopes are positive or negative. For example, the slope here is definitely a positive slope at -2, okay? So f of -2, the slope is positive, all right? At 0, that's a horizontal line when x is 0, and that has a slope of 0. So the slope when x is 0 is 0. And last but not least, at 3, this is a negative slope. So the slope at 3 is negative. And this is how we answer our question. This is going to be the smallest one because it's a negative value. This is going to be the biggest one because it's a positive value. And this one should be the one in the middle, or the mid value. So f of 3 should be the first one listed. Okay, so it can't be this one or this one. F of 0 should be in the middle. There we go. And f of -2 should be listed next. Your answer should be choice D. Typical calculator problem. I know that just by looking at the answers. Well, yes, we're on section B. I get it. But if this were on a review sheet and you're wondering, man, would I get a calculator for this problem? You would. Look at your answers. See how they're all 3 decimal places? They don't expect you to calculate that by hand. So, number 77 says, let h of x be the antiderivative, or the, yep, that's my marker that fell, kids. Let that be the integral, okay, h of x is the integral. I'm just going to make a little note here. That's the integral of this bad boy right here. Okay? If h of 5 equals pi, then what is h of 2? Oh, man, this is just a standard rule of integration and setup. All right? Once you set this up, it becomes cake because you just use the calculator. All right? Let's say that this is, I'm just going to call this f of x. Okay, this equation right here, this whole big thing. These are bounds, right? H means I'm taking the integral. So if I'm going to take the integral from 5 to 2 of this equation, which I'm just going to call f of x, I guess we'd have to say dx. Doesn't that mean, right? Doesn't that mean that I need to take my function with a 5 in it and then subtract my function with a 2 in it? It does. Okay? It really does. All right? So we know h of 5 is pi minus, they want us to figure out what this is. All right? So if only I could put a value of this on the left side here, then I could solve for h of 2. And that's exactly what I'm going to do. And I'm going to use my calculator to do that. All right? Oh, calculator, how I missed thee. All right? I'm going to take this integration of f of x, and I'm going to set the bounds of 5, and that's 2, not positive 2. It's positive, not negative 2, yeah. It's minus h of 2. So let's go math, and I believe number 9 says function int. That means my integral. Bottom bound is 2, upper bound is 5. And anytime I use a fraction, I like to use my fraction function. And I'm going to put this thing that they give us here, x cubed, pop out, plus the sine of x. Make sure you are in radians, over x squared plus 2 dx. Boom! So that should be 9.00825. Let's just bring this down here. So here we go. Put this off to the side. So I now have 9.00825 whatever. All right, well, let's subtract pi from this. Boom, I got to subtract pi from this value. And then that's going to equal negative h of 2 is going to equal this. Now let's do that in the calculator while we got it. We have our answer, and I'm going to subtract pi. Now it's 5.866666, so this is going to replace now. Boom. So it is 5.86666. I want to find h of 2, not negative h of 2. So let's just multiply this side by negative 1. Negative goes by. Multiply this side by negative 1, and I get negative 5.86666. And if I round that 3 decimal places, boom. There you go. So the calculator is crucial on some of these problems. There's no way you could have figured out that integral without the calculator. But on the previous problem, even though it's in section 1, part B, the calculator is pretty much useless. All right? Use it when you can, kids. Number 78. The continuous function f is positive and has a domain where x's are also all positive or greater than 0. If the asymptotes of the graph of f are at x equals 0, that's a vertical asymptote, at x equals 0, and y equals 2, it has a horizontal asymptote at y equals 2. Which one of the followings must be true? This is just testing you. Again, you can't use a calculator here. They don't give you the equation of the function f. They're testing you on your knowledge on how to solve asymptotes. Well, I know for horizontal asymptotes, it's a limit as x goes to either positive or negative infinity of my function, that should be 2. So let's look for that one right now. Okay, the limit goes to infinity is not 2, so that's not this one. Okay, limit goes to infinity is 2, that's good. Limit goes to infinity is 2, that's good. The limit of 2 goes to infinity, that's flipped. That's not good either here. So A and B are gone. They're bye-bye. So now I'm going to check my vertical asymptote. Now I teach my students to say whatever x value makes a function undefined. That does not cancel out of the problem. But the rule is I take the limits as I approach that value of 0 of the function, and that results in infinity. So it's not this right here. Okay, it is not this. As I approach 0, even from the right side, it's infinity. Choice C. All right, number 79. A file is downloaded to a computer at a rate modeled by the differential function f of t. Again, they don't give us an equation. We can't use a calculator here. Damn you, College Board. Where t is the time in seconds since the start of the download, and f of t is measured in megabits per second. Ooh, like technology. Which of the following is the best interpretation of f prime of 5 equals 2.8? Now, let me explain something to you here. They're asking you to interpret this statement in context of the problem. The file is downloaded to a computer, rate modeled by the differentiable function here. So this is the rate, okay, of the differentiable function, f of t, okay? T is time in seconds. So right here is my t. F prime of 5 equals 2.8. I'm just going to write, this is my t. So that has to be my time in seconds. So at 5 seconds, this is going to be part of our explanation. What is this 2.8? I don't know. Let's see. Okay. Since the start of the download, an f of t is measured in megabits per second. So it's going to be 2.8 megabits per second. And this is downloadable, right? A file is downloaded. So this file is downloaded at 2.8. So at 5 seconds, the file is being downloaded at 2.8 megabits per second. Let's see what our options are. Well, C and D are, say, over this interval. No, it's not at the, it's right at 5 seconds. There's no interval. So A says, at 5 seconds, the rate at which a file is downloaded to the computer is 2.8 megabits per second. Okay. And B says, at time t, the rate at which a file is downloaded to the computer is increasing at a rate of 2.8 megabits per second. All right. Here is the kit and caboodle. They tell us that the rate modeled by the differentiable function is this. So this is the rate. We are taking the derivative of the rate. Okay, so it's not the first, it's not this first one, which a lot of people would suggest, but it's increasing the rate of 2.8 megabits per second. Okay, so the file is downloading at 2.8 meters. It is downloading, it is increasing the rate at which it is being downloaded by 2.8 meters. Megabits, sorry. You can tell where my mind is. I've done so many calculus problems. Meters per second. No, megabits per second. That's the confusing part, and it's all because this little word right here. I mean, when I give this to my students, they always take A. But you have a rate, and the derivative of that rate would be the change in the rate given. Okay, so the answer is B. Got to be very careful when you read these things. Number 80. The function f has a first derivative given by this. This is the first derivative right here. Okay? On what intervals is the graph concave up? If it's concave up, that means the second derivative is positive. Okay? I'm going to use the calculator for this. Why not? Why not? I know the second derivative, okay, is the derivative of the first derivative, okay? Or I can replace derivative with slope. So if I want to figure out where the second derivative is positive, I can just figure out where the slope is positive of this graph, because the second derivative is the slope. Or I can graph the second derivative, which is crazy. I'll show you something even that I learned recently, and some of you guys might say to yourself, well, I already knew this, Visca. Well, good for you. I'm a teacher. I don't know everything. I love when I learn new things. And when I do, and I feel they're useful, I like to share them. Okay, so let's start with the graph of the first derivative. Boom. I'm going to go to y equals, which is right there, and I'm going to put in x to the fourth, and I'm going to subtract 6x squared, and I'm going to subtract 8x, and I'm going to subtract 3. So if I graph this, I put this in the first slot, so it should be the blue graph. Yeah, okay. Now, it's where this is positive. Let me drop down so I can see the bottom. You know, this graph should kind of come down here somewhere. I don't know. Let's, oh my goodness gracious. Oh, we'll just leave those lines there, I guess. Let's go to the window and drop that down a little bit. Go to -20. Let's graph that. See how far down that go. Oh, even further, you dirty dog, you. Go to the window, and let's change it, drop down even further. Let's go to -30. Boom. Come on, -30. Be the one, baby. Here we go. Oh, thank God. Okay, the only place this has a positive slope is from this point on. That's a positive slope, which means if this is the first derivative, the slope is the second derivative. It's positive from 2 to infinity, because it goes to the right forever. So I believe that my answer would be, if I get this out of the way, choice A, and that is the correct answer, okay? So I said there was a second way. I learned something new in the calculator. Let me just put this right here. Boom. Okay, that's from the number 2 right here, positive slope, okay? If I had the graph of the second derivative, I could just see where my y values were positive, all right? And I gotta tell you, my son, who's now in calculus, yeah, I got a son. I got a daughter too, great kids, but let's focus on this test, okay? And I bring my son up because he's like, you know, instead of taking the derivative manually, which would be easy, it'd be 4x cubed minus 12x squared minus 8. He said if you go to math 8, I'm going to take the derivative of what? Whatever's in y1. Vars, y, oh, I hope this works. It'd be crazy if it didn't. I'm going to take the derivative of y1 with respect to x, and I'm going to graph that in red. Come on, man. Where are you, man? It's spinning, man. I can see in that upper right corner next to the battery. There it is. Thank God it worked. All right. So let's take a look at this graph. Now, it's still spinning. I got to wait till that little yellow circle on the computer screen, on the calculator screen. There it goes next to the battery. Let's take a look at this. This might come in handy, and I think I'm going to show this to my students this year. All right. So we know the blue graph. It has a slope where from x is 2 to infinity to the right of positive. But if the red, okay, is the second derivative, okay, how do I know where the second derivative is positive? The y values on the red line represent the second derivative. Aren't y values all positive when you go above the x-axis? And they're all negative when you go below? So I want to figure out at what point is my graph, my second derivative, that red line, above the x-axis. Right here at 2, these are all positive y values on the red line, which means from 2 to infinity. So you could do it that way, and I think that's awesome that you can just graph the derivative of whatever's in y1, and you don't have to retype it out. That is cool. I like that. I like that a lot.